2019 paper 1 A-level chemistry AQA. Question 1. Complete figure 1 by writing formulas including state symbols of appropriate species on each of the two blank lines. So in this case it's going to be CS solid plus a half I2 solid. In this case this can be first ionization energy, so CS plus gas plus E minus plus I gas. That stayed the same because it's the first ionization energy of cesium, not iodine or iodide. So yeah, that's cool. Use figure 2 to calculate the standard enthalpy of atomization of iodine. So enthalpy of formation is minus 337. So it's going to be minus 337 plus enthalpy of lattice formation plus 585, and that's going to be equal to x plus 79 plus 376 minus 314. Should get enthalpy change as 107 kilojoules mole to power minus 1. Deduce what these values indicate about the bonding in cesium iodide. The value obtained by calculation is perfect ionic model is this of enthalpy of lattice formation for cesium iodide. Enthalpy of lattice for cesium iodide is minus 585. It should be use a perfect ionic model minus 582. So it is almost perfectly ionic. That's not a big difference of 3. If it was like minus 500 or minus 585, then it contains some covalent character. Use data to show this reaction is not feasible at 298 Kelvin. So first thing I need to do is delta S, entropy change of products, minus entropy change of reactants. So it's going to be, what I'm forming is C solid, so 82.8 plus a half plus 117 divided by 2 minus 130. That will give me 82.8 plus 117 divided by 2 minus 130, 11.3. Remember, delta S is measured in joules K to power minus 1 mol to power minus 1. Now that I've got that out of the way, I want to show this reaction is not feasible. So I'm going to use delta G is delta H minus T delta S. And I know that delta H is plus 337 kilojoules per mole to power minus 1. 337 minus temperature at 298 Kelvin, 298 times by delta S, 11.3. But that's in joules, so I'm going to divide that by 1000. And if I do that, 11.3 divided by 1000, I get 334. And that's obviously in kilojoules mole to power minus 1 because I'll convert delta H was already in kilojoules. I convert delta S into kilojoules because delta S is usually measured in joules K to power minus 1 mole to power minus 1, so divided by 1000 to convert to kilojoules mole to power minus 1. I get that, and obviously because that's greater than 0 is not feasible. Question 2. Describe post-electron deionization and give an equation. So describe the process. So P is dissolved in a volatile solvent, injected through a needle at high voltage, gains a proton. That's it. dissolved in a volatile solvent, injected through needle slash nozzle slash capillary at high voltage, gains a proton, H plus. And therefore the equation is just P plus your H plus, electrospray, you just gain a proton. So in the example, it would just be X grams for the equation, so you can apply it to anything really. That form XH plus. It doesn't ask for state symbols when you show it. What's the relative molecular mass of P? Well, P in this case, MZ value 546, but with electrospray we add 1. And then we get 556. Right? P is dissolved volatile solvent injected through needle at high voltage. Gains a proton. So I need to minus that 1 from that, so I should get 555. Calculate relative molecular mass of Q. Q, ionized electron impact, kinetic energy of that, ion takes this long, length is that, calculate relative molecular mass. So what I'm going to have to do is find out the mass. Now I can find out relative molecular mass. So mass is square root of 2ke divided by v. Times by 2ke. No, mass is 2ke divided by v squared. Yeah, that's the correct equation. And I don't have the velocity, but I know velocity is distance divided by time. So it's going to be distance, length of flight tube 1.50 divided by the time taken 1.23 times by 10 to the power minus 5. That will give me the velocity. Then I'll substitute that into here. So 2 times by kinetic energy, 2 times by 2.09 times by 10 to the power minus 15. Divided by the velocity, which I just put there, and obviously square it. So that'll give me the mass. Obviously in kilograms, in this case it's going to be in kilograms. Then I need to, so I get the mass as 2.81 divided by 10 to the power minus 25 kilograms. Now I want the relative molecular mass, obviously in grams. So first thing I'm going to do is, if I want to find molecular mass, I need to times it by Avogadro's constant. Why else would they give it me? So times by 6.122 times by 10 to the power 23. That will give me 0.169, and then times it by 1000 to get the molecular mass in grams. So 169. Say the meaning of the term periodicity. Repeating patterns slash trends of physical chemical properties. Repeating patterns slash trends of physical chemical properties. Identify the element in period 4 with the highest electronegativity value. So it's going to be bromine. Identify the element in period 4 with the largest atomic radius. It's going to be potassium. Reason being is that it's got the smallest number of protons and similar shielding as other elements in period 4. So it's going to have the largest atomic radius. So repeating patterns slash trends of physical chemical properties. Bromine is the highest electronegativity value in period 4. Potassium, largest atomic radius, smallest number of protons, a similar shielding as other elements in period 4. Name the property of arsenic 3 oxide that describes ability to react in these two ways. It's obviously going to be amphoteric. Amphoteric. And then just balancing this equation, so it should be 6 here, 12 here, 2 here, and 6 here, and also 3 here. 6, 12, 2, 6, 3. Question 4. I can't go through this. I haven't gone through aqueous and complex ions and all that. Yeah, transition metal complex. I haven't gone through that. Question 5. Yes, I can do this. Solid sodium chloride, NaCl, reacts with concentrated sulfuric acid. Which was forming HSFO plus HCl. The role of sulfuric acid in this reaction, proton donor, or you could say Bronsted-Lowry acid, but yeah, proton donor. Fumes of sulfur dioxide forms sodium bromide reacts with concentrated sulfuric acid. For this reaction, given equation, one of the observations state roles sulfuric acid. So sodium bromide reacts with sulfuric acid. Fumes of this is formed. Fumes of sulfur dioxide are formed. Oh, okay, so it's going to be this equation where you've got 2 NaBr plus 2 H2SO4 to form Na2SO4 plus Br2 plus SO2 plus 2H2O. The observation, brown gas, brown fumes, brown gas. And the role of sulfuric acid is an oxidizing agent. Oxidizing agent. In this case, oxidizing agent. In this case, it was a proton donor. Give the oxidation state of chlorine NaClO3 NaCl. NaClO3, oxygen minus 2 times 3 minus 6. Sodium is plus 1 plus Cl. So that's minus 6 plus 1 minus 5. That could be plus 5 to get overall oxidation, overall charge of 0. And neutral NaCl is just going to be minus 1. See, in terms of redox, what happens to chlorine in question 5.3? Redox, well, chlorine is oxidized and reduced. That's it. Give the formulas of D, E, and F. Well, I know D, silver nitrate solution, cream precipitate. So the bromide ions, silver nitrate solution. So it's going to be AgBr. AgBr. Formula E and compound E. But I also know your compound E, Ag2CO3, F, or bubbles of gas, F, well, it's obviously going to be carbon dioxide, that's very nice. And then ionic equation to form E. Well, to form E, it should be Ag2CO3, not an E. So to form it, this is actually a really easy question. Obviously, if you get this up to here, to form it, it's just going to be your Ag plus, so 2 of them, plus your 3O3, 2 minus. That's it. Equation showed the conversion of D, which is AgBr, into G. AgBr plus something to form G. And what is G? Complex ion G. I haven't gone through this. So yeah, but this is the equation. AgBr plus 2NH3r, or AgNH3 2 plus Br minus. Question 6. Calculate percentage of copper by mass in the alloy. Question 6. Question 7. Question 8, can do that as well. And question 9, I can do that as well. So 6, 7, 8, and 9. So I know to react this much with alloy with concentrated nitric acid to form a solution. Pour the solution in volumetric flask, mix the volume up to this much. Transfers 25 into conic glass, add excess potassium iodide, uses exactly this much sodium trisulfate. Okay. Calculate percentage of copper by mass in the alloy. So, if I find out the moles of sodium disulfate, I can find out the moles of iodine. Then I can work out the moles of copper iodide. Then I can work out the mass, and then I can also use to work out the mass over the total mass. Okay, so look at the moles of Na. In this case, the S2032 minus 9.00 times by 0.0800, and obviously divided by 1000 to convert into moles per minus cubed. That will give me 7.20 times by 10 to the power minus 4 moles. And I can see from the equation the moles of S2032 minus the same as the moles of 2Cu2 plus. So not iodine, actually, just Cu2 plus. So that's the moles of Cu2 plus as well in 25 centimeters cubed. 25 centimeters cubed conical glass, and then use that. But I want it in 250 centimeters cubed, so I need to times it by 10. And that will give me 7.20 times by 10 to the power minus 3 moles of Cu2 plus. This. Then I know it's a 2 to 2 mole ratio, therefore I can work out the mass of copper. 2 to 2 mole ratio is the same. So moles is mass of Mr. Mass is going to be the moles. Moles 7.20 times by 10 to the power minus 3 times by the Mr of copper 63.5. That will give me 0.457 grams, and I know the total mass is this in milligrams. But I want to convert it to grams, so I need to divide by 1000. So 0.985. Times by 100, 46.4%. Yeah, perfect. 46.4%. So there's two ways you can reduce percentage uncertainty in measurement with using the same apparatus. Use more of the alloy, or use more of the alloy, use a lower concentration of the thiosulfate solution. Say the role of iodine reaction with sodium thiosulfate. Iodine reaction with sodium thiosulfate. It's going to be oxidizing agent. Oxidizing agent. Give the full electron configuration of copper 2 plus ion. Oxidizing agent. 1s2, 2s2, 2p6, 3s2, 3p6 3d9. Explain why copper iodide is white. What kind of questions are? Well, it's got a full 3D subshell. Therefore, no. Oh, this is. I haven't gone through this. I have gone through it by myself. So no D transitions possible. Cannot absorb visible light or white light. Iodine vapor is easy calculate volume at this much occupies. So I'm going to have to use PV equals nRT. I want a volume, so volume is nRT divided by P. I want to find out the volume of iodine vapor, so the moles will be 5 divided by the mol of this, 253.8. Times by 8.31 times by the temperature in Kelvin. I need to add 273, so 185 plus 273 divided by the pressure in Pascal, so 100,000 pascals, so I need to times this kilopascal by 1000. Now I want it in centimeters cubed, but remember it's dm cubed meters cubed dm cubed centimeters cubed. Dm cubed is always in the middle. How I like to remember that is the D block of the periodic table is always in the middle, so it's dm cubed. So to go from meters cubed to dm cubed, I'm going to have to times by a million. So I get that times by a million and I get 750 cm cubed. Just one thing I need to check though. Yeah, iodine vapor, so it's going to be I2, so the mol is going to be of I just times by 2. Question 7, calculate mass of oxygen gas in equilibrium mixture, and I know sulfur dioxide decomposes in heating to an equilibrium mixture containing sulfur dioxide and oxygen. Alhamdulillah. Okay, and I know equilibrium mixture contains this much of sulfur dioxide. So well, I don't care about the mass of sulfur dioxide. I need to find out the moles. Equilibrium moles. So moles of SO2 is 6.08 divided by the m of SO2. Sulfur 32.1 plus 16 plus 16, I'm pretty sure. That's the moles of SO2. Remember, for that is the equilibrium mixture contains this much of sulfur dioxide, and then therefore that's going to be 0.0949 moles. Therefore the equilibrium moles of oxygen is going to be 0.0949 divided by 2, because 2 to 1 mole ratio, 0.0474. And I want a mass of oxygen gas moles and mass of mol. Mass is going to be the moles times by the mol of oxygen gas, which is 16 plus 16, which is 32, and I should get 1.52. Bit of a weird question. Question 7.2, calculate mole fraction of each substance at equilibrium. Give the expression for Kp, calculate total pressure. So, mole fraction of SO3 is going to be, first thing I would do is calculate total equilibrium moles. These are obviously the equilibrium moles. Total equilibrium moles 0.320 plus 1.20 plus 0.600, 2.12. So it's just going to be 0.320 divided by 2.12, 1.20 divided by 2.12, and 0.600 divided by 2.12. Then it says give the expression for Kp. Well, Kp is curly brackets product, so it's going to be partial pressures of the product, SO2, 2 moles of it, so it's going to be squared times by partial pressure of O2, just 1 mole, so it's just like that, divided by the partial pressure of SO3 squared. In this case, it should just be P. Then it says calculate total pressure. So what I'm going to have to use instead is a mole fraction. So it's going to be rearrange it to calculate total pressure. How do I do that? Well, total pressure is going to be Kp times by the mole fraction of SO3 squared divided by the mole fraction of SO2 squared times by the mole fraction of O2. That's what it's going to be. Obviously, I should have simplified these as well to 0.15, 0.57, 0.28. So that's what I'm going to shift you in, rearrange it. And how do I get P? Where does P come from? Well, all I'm doing is, I know Kp is that, so I just times by that and divide by that. So P is just going to be all of this. So Kp times by mole fraction SO3 squared divided by mole fraction of SO2 squared times by mole fraction of O2. I should get 1.91 times by 10 to the power 5 pascals. (7.3) Explain how this reaction can be deduced that the forward reaction is endothermic. Well, I know at a higher temperature, Kp is bigger. At a lower temperature, Kp decreases. So that's what I'd say first. Kp is higher at higher temperatures. My first mark. Because at higher temperatures, more. Well, why would Kp get bigger? Well, at higher temperatures, more products are formed, so equilibrium shifts to the forward / right direction, which makes sense. If Kp is getting bigger, I'm going to have more products divided by the same amount of reactants. So you can shift to the right hand side, more products are formed. There we go. Calculate value of Kp at 500 Kelvin for the equilibrium represented by this equation. Use data from question 7.3. Question 7.3 tells me calculate the value of Kp at 500 Kelvin. At 500 Kelvin, equilibrium constant Kp is that. This equation and this equation. So I've gone from, I'm not reversed it, like normally they reverse it. I expect you to do that. What I've done is basically all I need to do here is square root 3.94 times by 10 to the power 4, which is 198.5. And therefore the units, well, the units in this case was PA, square root of PA. PA is the power of 1, and so remember square root of x equals x to the power of a half. So therefore square root of PA is going to be PA to the power of a half. Question 8. Draw a diagram to show the strongest type of interaction between two molecules of ethanol, C2H5. Obviously, I'm going to show the oxygen with that delta negative, and it's got this H plus. And then I draw another molecule of this, which has also got this H plus, and it's also got this C2H5. And there we go, there's attraction to the lone pair. And that's it. Delta negative, two lone pair of electrons, there H plus. Attraction to this lone pair of electrons on oxygen, which is delta negative, should show that as well. That's delta positive. So the molecular force involved, explain the differences in boiling points. Well, ethanol and methoxymethane. Hydrogen bonding in methanol. What about methoxymethane? Is it also hydrogen bonding? No, because hydrogen bonding is the attraction between the lone pair of electrons on an oxygen atom and the NOF atom. So this CH3CO CH3 is going to be like this. Something like that, right? So it's not bonded to a hydrogen, it's not bonded to an NOF atom, it's bonded to a carbon, so it's not going to have hydrogen bonding. So that's the first thing. So I'd say ethanol, well, I'd say actually hydrogen bonds, start off with hydrogen bonds between ethanol molecules. And van der Waals forces between methoxymethane molecules. Hydrogen bonds are stronger. I could also say stronger intermolecular forces compared to van der Waals forces, which are between the methoxymethane molecules. That's extra space, that's fine. Go to the shape of the POCl3. So POCl3 phosphorus and 4 attached to 4, that's fine. ClF4 minus was Cl, F, 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 and F. Well, chlorine's in group 7, bond to 1, 2, 3, 4, and it's also got this minus charge. So I'm going to have lone pair of electrons here, lone pair of electrons here, 1, 2, 3, 4, 5, 6, and then this negative charge will add another one, so that'll be 7. Name of shape of POCl3. 4 bonding pairs, no lone pairs. Tetrahedral, and with ClF4 minus is going to be, well, it's got 4 bonding pairs, 2 lone pairs, so it's not going to be octahedral. That's 6 bonding pairs, lone pairs. So it's going to be square planar, and the bond angle and the square planar 90 degrees. Question 9. For pure water at 40 degrees Celsius, pH is 6.67. A student thought that the water was acidic. Explain why the student was incorrect. Because the concentration H plus sign is equal to the concentration OH minus signs. Because remember, it is pure water. Determine the value of Kw. Kw is obviously going to be this, the original expression. But in this case, I've got pure water, so it's going to be Kw equals concentration H plus squared. And I'm going to tell the examiner because the concentration H plus sign equals the concentration OH minus signs. Therefore, H plus squared. I want to find out the value of Kw. I don't want to find pH, sorry. Value of Kw is just going to be concentration H plus ions, which is what? Well, I've got the pH 6.67, and I know, or I should know, concentration H plus ions is 10 to the power minus pH. Therefore, it's 10 to the power minus 6.67. Therefore, Kw is 10 to the power minus 6.67 squared. And that's my final answer. (4.57 times by 10 to the power minus 14). And that, all of that for 4 marks. Pretty nice. 9.2. Use figure 4 to determine the value of Ka for propanoic acid at 25 degrees Celsius. 25 degrees Celsius. Obviously, this is the propanoic acid at this. So, value of Ka for propanoic acid. And I know sodium hydroxide was added gradually from a burette to this much propanoic acid. So, I want to find out the value of Ka. Okay, so first things first, obviously, I need to look for the volume at half equivalence. So, it's going to be here. So say 19.9, sorry, 19.5. Yeah, because I'm looking at it here. So 19.5 divided by 2, 9.75, and this is obviously the volume at half equivalence. Equivalence 9.75 centimeters cubed. And I also now want to find out the concentration of H plus ions. No, sorry, I want a pH. The pH is going to be I'll just read off the pH because I know, yeah, 19.5 here, so I just read off the pH at this. So I should get 9.75 centimeters cubed, and then read off the pH, so lie around about 4.95. Therefore, to find out a Ka, well, Ka in this case is just going to be actually, I think there's a better way of approaching this. I think this is just confusing for myself and for you guys as well. Let's try a different method, alternative method. So I know that sodium hydroxide added gradually, but remember, here is when I've got 0 sodium hydroxide, so this is the pure acid. So if it's pure acid, Kw H plus ions is equal to A minus ions. So therefore, it's going to be h plus squared instead of h plus a minus divided by ha. H plus squared divided by ha, and that is because this is pure acid. 0 centimeters cubed of sodium hydroxide was added. So I just read it from the graph. The pH is 3. Therefore, concentration H plus ions is 10 to the power minus pH, which is 10 to the power minus 3. So it's just going to be 10 to the power minus 3 squared divided by HA, concentration of HA of propanoic acid, which is at 0.080. 0.080. And I get 1.25 times by 10 to the power minus 5 moles per minus cube. Suggest which indicates the most appropriate for the reaction, question 9.2. So if I look at the here, so obviously 1 for 9.75, because I got a volume at half equivalence 9.75, so it's got to be in the half equivalence point indicator. So 9.75, so it's going to be Krizov-Failing, because that's 8.2 to 9.8. 9.75 is in there. Question 9.4. Student prepared. Okay, this looks very difficult. Student prepared buffer solution by adding this much of salt, this much of weak acid, and mixing thoroughly. Student added this much, then added. Okay, so I'm going to work with it in steps. So obviously it's already pH, so I already know pH 2 decimal places anyway. So first thing I'm going to do is work out the moles of HX, which is concentration times by volume. And if I do that, I get 0.05. Then what I want to do, well actually I already got the moles of the salt Kx, 0.0136. Kx of the salt. So I'll say HA plus OH minus divided by A minus plus H2O. In this case, 0.05 HX of the weak acid, the salt 0.0136, Kx 0.0136. Which one's bigger? It's obviously going to be 0.05. So it's going to be 0.05 minus 0.0136. That's obviously going to be 0. And then therefore on the right hand side, I'm going to add 0.0136. Now, H2O, I don't really care about it because it's not in the Ka expression. Okay, now I've got that. That is what? That's the moles. So, just want to clarify that. Because ultimately, when we want to find out, obviously we're going to have to construct the K expression, rearrange it to find concentration H plus. I need concentrations, not the moles. Okay, but obviously the volumes will cancel out, but yeah, let's carry on. Then I added sodium potassium hydroxide solution, so it's going to be what was it again? This is a specific equation that I had in my school workbook, so I'm going to have to flip through that. I can't find it. Inshallah, I'll find it. Allah wills. Okay, I just think I don't think I think it's the same anyway. Okay, so I've got this. Then I know this much of potassium hydroxide, and then this is the moles. So the moles of potassium hydroxide is 3.00 times by 10 to the power minus 4. It usually gives me concentration and volume. I need to calculate the moles, but in this question it's already giving me the moles. Then what I need to do is then reconstruct this HA-OH minus expression. So HA plus OH minus to form A minus plus H2O. And the concentration HA is 0.0364 moles of potassium hydroxide. Potassium hydroxide is only got 1, so I don't need to worry about times that by 2 or anything. It's only got 1 hydroxide ion, so then this is 3.0 times by 10 to the power minus 4, and A minus is obviously going to be 0.0136. Then I subtract by small as well. Obviously, it's going to be 0.0364 minus 3.0 times by 10 to the power minus 4, because 3.0 times by 10 to the power 3.00 times by 10 to the power minus 4 is smaller than 0.0364. So that's going to be 0 minus 3.00 times by 10 to the power minus 4. That would give me 0.0361. And then this case on the right hand side, I'm going to add it 0.0136 plus 3.00 times by 10 to the power minus 4, 0.0139. Now I'm going to have to use space here. I'm going to have, I guess I could do it here, 9.4. Now I know obviously Ka is H plus A minus divided by HA. Concentration HA. I want to find H plus because ultimately I want pH, and pH is minus log 10 H plus. So H plus equals Ka times by concentration HA divided by the concentration of A minus. And I know Ka is that. And also, this is a key fact now. Obviously, I could show because concentrations these moles divided by the volume, because concentration moles of concentration volume, concentration moles divided by volume. But in actual reality, the volumes will cancel out. So I can just say it's going to be 1.41 times by 10 to the power minus 5 times by the moles of HA, because volumes will cancel out anyway, 0.0364 divided by 0.0136, and that gives me the concentration H plus sign. But I'm not done there. I want the pH, and pH is minus log 10 of the concentration H plus signs. Therefore, whatever that I got in the calculator, I just say minus log 10 of my answer. I get pH as 4.242, which is wrong. So I did something wrong. Just check the mark scheme now. So I got this correct. What I did wrong was I overcomplicated it. I shouldn't have done this. This was no point. Instead, what I was supposed to do is, because then I added this much potassium hydroxide, just minus potassium hydroxide in this case, add potassium hydroxide for this. I get 0.0497 and 0.0139. 0.0139, and then I do the exact same thing, rearrange expression H plus, substitute it in, I get pH minus log 10 at H plus, I get 4.30. It's a shame I didn't get it correct, but yeah, because it's already given us the moles of this, and then added this, so I don't need to work out after this, because that's not how you do it. So I need to subtract potassium hydroxide, add potassium hydroxide, and you get that. Okay, I get it now. And then it says use a buffer solution has constant pH even when diluted, use a mathematical expression to explain this. Because the concentration of this and this are very, very similar. So let's say in this case the ratio of, not HA, in this case it's HX, ratio of HX concentration over concentration of X minus remains almost constant. And that is the end of this paper.